In this section, you'll learn about the basics of the different Cisco devices that are available. We'll cover hubs and switches, how they are similar to each other, and also the differences before we move on to routers and also how routers compare to your switches. And then finally, I'll cover the different platforms that are available that aren't really covered in the routing and switching track, such as firewalls, wireless LAN controllers, telepresence, etc. So the information that we're going to cover here is going to give you the foundation you need before learning the more advanced topics on the devices in the later sections. In this lecture, you'll learn about the basics of hubs and switches, and I'll do a comparison between the two. The functions of hubs and switches are very similar. You take your end hosts in your local area network, like your PCs, your servers, and your printers, and you plug them into a hub or a switch with an Ethernet cable, and those end hosts are then able to communicate with each other through the hub or the switch. In the picture here, we've got a Cisco 2960 Catalyst switch. It's a 48-port model, so obviously you could plug in a maximum of 48 hosts into that switch. But what if you've got more than 48 hosts in your campus, which you probably will have? Well, in that case, you're going to have multiple switches in your local area network, and your switches will be connected to each other with Ethernet cables again. That's your inter-switch links. So I said we were going to compare hubs and switches. We'll have a look at hubs first. Hubs always operate in half-duplex mode. That means that the attached hosts can either send or receive data. They can't do both at the same time. All of the hosts that are plugged into that hub share the same collision domain, meaning that only one device can transmit at a time. If two devices do transmit at the same time, then they will detect that and they'll back off, and they will then resend to make sure that there's not another collision again. The method that is used for detecting and recovering from collisions is CSMA-CD. That's Carrier Sense Multiple Access with Collision Detection. Okay, so hubs, half duplex, and a shared collision domain. With switches, on the other hand, they can operate in either full duplex or half duplex. And in practice, they're always going to operate in full duplex mode because that's much more efficient. When they are operating in full duplex, the attached hosts can both send and receive data at the same time using their receive and transmit wires. Also, all hosts have their own dedicated collision domain. So because of that, we're not going to have collisions. A collision detection mechanism is not required. Looking at the OSI stack, switches operate at layer 2. Our hubs operate at layer 1. So hubs, they're not MAC address aware. And whenever a frame is received on a port, it's flooded out to all the other ports apart from the one that it was received on. And because of that, all hosts that are plugged in there are going to receive the frame, so they're going to have to process it, at least as far as seeing that it's not for them. Switches, however, operate at layer 2 of the OSI model. They also operate at layer 1, obviously they've got physical ports on there. This means that switches are MAC address aware. Whenever a frame is received, the switch will look at the source MAC address in the layer 2 Ethernet header, and it will learn that MAC address. It will then add that MAC address to its MAC address table, which is a mapping between the MAC address and the port that it is reachable on. If a unicast frame is later received where that MAC address is the destination, the switch will only send out the relevant port, unlike a hub that floods it out everywhere. This is better for performance and security, as frames only go where they are required. Whenever a frame is received for the broadcast address or an unknown unicast address, it would be unknown because the switch hasn't learned about it yet. It will be flooded out all ports apart from the one it was received on. Okay, so that was the basics of hubs and switches and the difference between them. We'll be having a look at switches in a lot more detail as we go through the other sections of the course. We're not really going to talk about hubs anymore, because hubs aren't used anymore. Back in the day, like 15 years ago, hubs were commonly used because switches were very expensive. Switches have come down in price so much now, though, that you can't even buy hubs anymore. Switches are always used. In the last lecture, you learned that switches, which function at layer 2 of the OSI stack, learn MAC addresses and use that information to populate the MAC address table, which is a mapping of the MAC address to the port that it is reachable on. In this lecture, we're going to take a look at how that works in a bit more detail with an example. So we've got one switch here. We've got a host with MAC address 1111.1111.1111 plugged into port 1. I've just written it in shorthand here as 1.1.1 to keep things a bit more simple. 2.2.2 is plugged into port 2 and 3.3.3 is plugged into port 3. Right now we've just powered everything on, so there's nothing in the MAC address table yet. Then the host on the left, 1.1.1, sends a frame in with the destination MAC address of 2.2.2. So the switch will see that. It sees a frame coming in with the source MAC of 1.1.1, the destination MAC of 2.2.2, so it learns that 1.1.1 is reachable on port 1, and it puts that information into the MAC address table. The destination of 2.2.2 is not in the MAC address table yet, so it's an unknown unicast address, so the switch will flood it out all ports apart from the one it was received on. So that will be sent out ports 2 and 3. That will be received by both hosts. The host 3.3.3 will see that the destination MAC address is 2.2.2. That's not it, so it will just silently discard the frame. The host of 2.2.2 in our example is going to send some traffic back. So it sends a reply from the source MAC of 2.2.2 itself to the destination MAC address of 1.1.1. That will hit the switch again. The switch will see that traffic has come from a source of 2.2.2 and it came from port 2, so it will put that information into its MAC address table. It will then send the frame out only port 1 because it sees that the destination MAC address is 1.1.1 and it knows that it's available on port 1, so it sends it out only that port. Okay, so that was how traffic works with a single switch. Now we're going to look at another example where we've got two switches. So switch 1 has got host 1.1.1 plugged into port 1 and 2.2.2 plugged into port 2, and switch 2 has got host 3.3.3 plugged into port 1 and 4.4.4 plugged into port 2. And the two switches are connected to each other using port 24 on both switches. Again, we've just powered everything on, so there's nothing in the MAC address table on either switch yet. Then host 1.1.1 sends a frame in with a destination MAC address of 2.2.2. Switch 1 will learn that 1.1.1 is available on port 1 and it will put that information into its MAC address table. It will then flood the frame out all ports because it's unknown unicast. It doesn't know where 2.2.2 is yet. So that will get sent out both port 2 and port 24. When it comes into switch 2, switch 2 will do the same thing. It will flood out all ports, so that will be sent out port 1 and port 2 as well. The hosts 3.3.3 and 4.4.4 will see that the destination MAC address is 2.2.2. That's not for them, so they will silently drop the packet. While that is happening, switch 2 will update its MAC address table because it learned that 1.1.1 was reachable through port 24 because that's the port that the frame came in on. The frame will have reached 2.2.2. In our example, again, it's going to send some return traffic, so that will hit switch 1 with a source MAC of 2.2.2 and a destination MAC address of 1.1.1. Switch 1 will update its MAC address table with the entry for 2.2.2 to say it's reachable on port 2. Switch 1 will then forward the frame out port 1 because it already knows that MAC address of 1.1.1 is reachable through there. It's in its MAC address table. Notice that the frame does not get sent down to switch 2 now because switch 1 knew that it should go out only on port 1. The next thing that happens is we're going to have some different traffic. So now the source of 3.3.3 sends a frame to destination MAC address of 2.2.2. That hits switch 2 and it will update its MAC address table to say that host 3.3.3 is reachable on port 1. Switch 2 will then forward that frame out all ports because the destination MAC address was 2.2.2 and it doesn't have that in its MAC address table. So it's unknown unicast, it will send it everywhere. That will hit switch 1 and switch 1 will see the frame arriving on port 24 that came with a source MAC address of 3.3.3, so it will put that information in its MAC address table. It will then send the frame out port 2 to the destination of 2.2.2 because it already had that in its MAC address table. It just sends it out that one relevant port. Then host 2.2.2 sends some return traffic back to the destination MAC address of 3.3.3, and that hits switch 1. Switch 1 does have 3.3.3 in its MAC address table. It sees that it's reachable through port 24, so it sends it out just that port. The traffic will then hit switch 2. Switch 2 sees traffic coming in from a source MAC address of 2.2.2 on port 24, so it will update its MAC address table with that information. It will then forward the frame out port 1 only because it knows that 3.3.3 is available out that port. And if you look at the MAC address table for switch 2 now, you can see that 1.1.1 and 2.2.2 are both reachable on port 24. And this is what you'll see in normal practice as well. Where a switch has got a single end host plugged into it on a port, then it will just have that one MAC address on that port in its MAC address table. But where a switch is connected to another switch, you'll see there will be multiple MAC addresses reachable on that port. Okay, that's it. That's what I wanted to show you there. You now know how switch operation works, both for a single switch and in a multi-switched campus. In this lecture, you'll learn about the basic operation of routers and how they compare to switches. Routers route. That's why they're called routers. And what that means is that they can direct traffic between your different IP subnets. They're required to do that. To be able to route traffic from one IP subnet to another, you're going to need a router to be able to do that. So they route traffic between our different IP subnets. IP is at layer 3 of the OSI stack, so a router operates at layer 3 of the OSI model. Obviously, it has physical interfaces on there as well, so it's also operating at layer 1. It also needs to understand layer 2 addresses, so it also operates at layer 2 as well. And routers actually will normally be aware up to layer 7 for advanced functions as well. But when they're doing the job of routing between different IP subnets, they're operating at layer 3, so routers are termed as a layer 3 device. To compare them with switches, routers are layer 3 aware and can route traffic between different networks. Switches are layer 2 aware, they're not layer 3 aware, and can switch traffic between hosts on the local area network. Routers support many different types of interfaces, such as Ethernet, serial, ISDN, and ADSL. Switches will typically only support Ethernet interfaces. Switches will typically have a lot more ports than routers, and switches forward broadcast traffic. Routers don't forward broadcast traffic by default. So let's go back a slide. A couple of the things that I said there are that routers support many more different types of ports than switches, and they'll usually have less available ports than switches. So if you remember, we had a look at a Cisco Catalyst 2960 switch, which had 48 ports when we did the basics of switches. So it had 48 ports plus some uplinks on there, and they were all Ethernet ports. If you have a look at the picture here, this is a Cisco 2800 series router, and it's only got 2 built-in Ethernet ports. You see there's 4 ports there, but one of them is a console port and another one is an auxiliary port. So it only comes with 2 Ethernet ports compared to our 48 port switch that we had a look at earlier. But if you look to the right of those ports, you see that there are modular slots there. So we can buy different types of interfaces such as ADSL, Ethernet, etc., serial ports, and we can put them into the router. Okay, moving on, let's have a quick recap of switch operation. So in the diagram here, you can see we've got a building, we've got a couple of switches in there. All our hosts are on the 10.10.10.0/24 network. When that's the case, they can all communicate with each other through our switches. When they're all on the same IP subnet, there's no need to have a router there. But if one of those hosts had the IP address 10.10.11.10/24, it's now on a different IP subnet, and it's not going to be able to communicate with the other hosts on the 10.10.10 network if we only have switches there. It's in another layer 3 network, so we need a layer 3 device, our router, to be able to route traffic between those hosts. So we put a router into the infrastructure now. It's aware of the 10.10.10 and the 10.10.11 networks, and it's going to be able to route traffic between all the hosts on the network now. Okay, one other thing to tell you about here is that you can get advanced switches which are layer 3 aware and can route traffic between different IP subnets. When you get one of those layer 3 aware switches, it's known as a layer 3 switch. It still has a lot of characteristics that are similar to a normal switch though, in that it will typically only support Ethernet interfaces and it will usually have more ports than routers. So looking at our diagram again now, you see that we only have switches in the network infrastructure, but the switch at the bottom is a layer 3 switch, meaning it is layer 3 aware. It's aware of the 10.10.10 network and the 10.10.11 network, and it's able to route traffic between them. Now, you can actually do this on a Catalyst 2960 like you saw earlier. Again, way back in the day, layer 3 switches were expensive, but they've come down in price now. So it is very common to have layer 3 switches routing the traffic which is within the different subnets on your local area network. However, if your connection outside that campus, out to the wide area network, is using an interface type which is not Ethernet, then you would still require a normal traditional router for that traffic as well. In this lecture, you'll learn about the other main product offerings that Cisco have other than their routers and switches. The Cisco firewall is the ASA. That's the adaptive security appliance, and you can see a picture of one of those here. The IPS, the intrusion prevention system from Cisco, is the SourceFire Firepower IPS. That can be bought either as an appliance, or more commonly now it will be either a software or a hardware module that lives inside the ASA firewall. Cisco also make wireless products as well. They have wireless LAN controllers that you can see on the left here, and wireless access points that you can see on the right. The reason that they have wireless LAN controllers is that you get better scalability when you deploy those rather than having just lots of standalone wireless access points. For collaboration, Cisco have Unified Communications Manager. That is a software product which is an IP-based PBX. So it replaces traditional PBXs, private branch exchanges, which controlled the phones that you would see in buildings a long time ago. A lot of modern companies still are using traditional PBXs, but IP PBXs are getting more and more popular. Cisco's Unified Communications Manager is one of the most popular IP PBXs that are available. If you are going to be using the Cisco UCM to control your phones, you're also going to need to have IP phones on your desks. So Cisco produce those as well. You can see a picture of a typical Cisco IP phone on the left here. Cisco also do high-end, high-definition video conferencing systems. That's Cisco Telepresence, and you can see a picture of one of the available Telepresence models on the right of the picture. Another really popular product that Cisco have is Cisco WebEx, which is used for meetings. Finally, there's also data center. You can see a picture of the UCS Blade server on the right here. UCS stands for Unified Computing System, as well as the Blade server that you see here. Cisco also have standard rack mount servers as well. So with the UCS, Cisco moved into offering compute as well, where you can actually run your servers directly on Cisco hardware. The other main product that Cisco have for the data center market is the Nexus switches. These are very similar to the standard Cisco switches which run the iOS software. They do exactly the same job, but these are often a bit higher end switches, and they run the NXOS software instead. The commands in NXOS and iOS are very similar though, so after you've learned the information on switching in this course, you can pretty easily take those skills across to the data center as well.